So as part of Visual C++, we've got a couple very interesting features there. The first one is the safe CRT library extensions. So when the C runtime library was originally designed and implemented by the community, we had a very different set of concerns than we have today. Performance was foremost in people's minds. Networked environments where security was really foremost in people's minds. It really wasn't the situation at that time. So as a result, we ended up getting these APIs that are used by C++ developers in a way that's kind of insecure by default, right? For example, you've got output buffers that you're passing to these CRT library functions, and you don't pass the size along with them. So the CRT library functions can go ahead and overrun a buffer and have no way of knowing that it was doing that, because all it knows is an output buffer and how much you told it to write. So in Visual C++ 2005, what we did was audit the entire CRT library. And we looked for all of those functions that tend to lead to programming problems when they're used in the way that everybody expects to use them. And for all those functions that had problems, we fixed them. And there are a couple of ways we fixed them. In some cases, all we had to do was add some extra parameter validation to the existing implementations. But in other cases, we actually had to provide new APIs. So pretty much any case where you've got an output buffer with new safe CRT library extensions, you're going to have a buffer plus the output size for that buffer. So it's not going to solve all problems, because it's still possible that the customer or the developer could put the wrong output size in there. But by default now, you're going to be thinking about those sorts of things when you program against these APIs. The existing non-safe extensions, or the non-safe parts where there are safe extensions, have been deprecated. So one of the big changes people are going to see when they use Visual C++ 2005 and they recompile their existing apps is they're going to get a whole bunch of deprecation warnings for every place where they're using a potentially unsafe CRT API. And fixing those is mechanical, it's fairly straightforward, but doing that will probably expose some issues that people had in their code and never actually realized they had in their code. One of the other cool things...
You deprecated only the ones that came up in the audit, or the entire...
So we've deprecated anything that we've provided a new version for. So wherever we've had to provide a new API that takes, for example, extra parameters, we've provided an _s version of that function. And wherever there's an _s version, if you use the non-_s version, you end up getting a deprecation warning. That can be turned off if you decide that you don't have the resources or aren't interested in making your code more secure. We certainly don't recommend that you turn it off, but it is available if absolutely necessary. One of the other cool things is that we're working actively with the standards community in order to try and get these extensions or some version of these extensions standardized. So we've actually gotten pretty far along with that, and all the proposals are publicly available. And in the forum on the video, I can go ahead and post a link to what's available right now.
Outstanding.
The second piece is, so that's writing your program so that it's going to be more secure by default. The next piece you can think about is, all right, so I've written my program, I may or may not have made mistakes. Now how do I find problems? This does get into the separate tool space, where we're going to be shipping some of our static analysis tools as part of the Enterprise Architect SKU. And you'll be able to run that, and it'll pick out all sorts of common errors that lead to problems like uninitialized variables, potential buffer overruns, things like that. And the kind of the final piece of the story is, so I've written my code so it's more likely to be secure. I'm using my APIs securely by default. I've gone ahead and ran my static analysis tools to make sure I haven't made the common programming mistakes, but I still might have had some things that slipped through the cracks. That's where our /GS security protection comes in. By default, in Visual C++ 2005, new projects will come with /GS. In fact, by default, the compiler will add /GS protection. What this does is it instruments the stack frame for C++ functions to contain a cookie that protects the return value, which is the most return value, and actually in Whidbey also function arguments that are pointers. And if you do a buffer overrun and potentially overwrite one of these, which then can cause exploited code to run, we can detect that because that means the cookie has also been overwritten. So after we exit the function, we check to see whether or not the cookie was overwritten. If it was, we just go ahead and terminate the process or call a custom handler. If it wasn't, we know that in all likelihood, and we've taken great pains to make sure that people can't figure out what the cookie is and spoof it. In all likelihood, there hasn't been a buffer overrun. Now, we don't cover all cases, but every version we get better. In fact, if the 2005 GS protection had been available, it would have prevented the spread of blaster, slammer, code red, pretty much all of the high-profile worms that were based on buffer overruns that have come up in the news lately.
So what's the downside to that?
So the only real potential downside there is that it can have a small performance impact. One of the things that we do in our optimizer is...
So you're doing the right cookie and the cookie checks.
Correct. It's the cookie is stored in a global place, so we can...
At all your calls?
In the prologue and the epilogue for every function. So in the part of the code that sets up the stack and tears down the stack, that's where the cookie insertion and check happens. It's something where we actually do a lot of work in the optimizer to figure out whether or not these things are necessary. If you don't have a buffer on your stack, or you're not having any code that manipulates the stack directly, as far as writing into something that looks like a buffer, you actually don't need this protection. So we can optimize it away in cases like that. But this is something that we're throwing on every major product that Microsoft ships.
Did you do maybe like more liberal use of inlining or anything like that to solve it as well? I heard there was some feature of inlining that I was wondering.
So we tune our optimizations, including inlining, for every release. There was some tuning that happened here. I think I might know what you're talking about with inlining, but I'm not sure it's related to this specific thing. But from a performance perspective, there's really no question that the protection you get is worth the pretty much negligible performance impact. Every major Microsoft product agrees with that. Windows Server 2003 has shipped with GS protection on. Visual Studio has GS protection on. Office is using it.
So just to step back, those were compiled with the WAC-GS, right? So the whole operating system was compiled with WAC-GS.
Most of the operating system.
Most of the operating system.
Only about 300
Task. Yeah. So there was a recent buffer overrun that just came out that didn't hit Windows 2003 probably for this exact reason.
Exactly.
It was a buffer overrun in Task Scheduler, and it did not hurt 2003.
And that was due to the GS protection.
Absolutely.
Yep.
Way to go.
And this is and this is something, just to be perfectly clear, you ship your applications with /GS, and we recommend that everybody does that, because it is the last line of defense against buffer overrun and similar attacks.
So like the TCP.